Welcome to Section 7 of Introduction to Image Processing. This section introduces clustering as a method of image segmentation. Clustering refers to organizing a set of objects into groups of similar objects. For example, this input shows using the general-purpose findClusters function in the Wolfram language to organize a set of colored squares into 3 groups of elements with similar colors. Clustering the pixels of an image works in much the same way, except that the things to be clustered are pixels in an image rather than elements in a list. For example, here is a 9x4 image composed of those same 9 colors. The pixels of this image can be organized into clusters using the clustering components function. The result is a 9x4 matrix called a label matrix. The clustering is the same, but instead of collecting the elements of each cluster in separate sublists, as in the result from the findClusters function, the clusters are identified by integers in the label matrix. The label matrix has the same dimensions as the image, and so for every pixel in the image, there is a corresponding integer in the label matrix. Pixels in cluster 1 are identified by a 1 in the label matrix, pixels in cluster 2 are identified by a 2 in the label matrix, and so on. For larger examples, rather than displaying the label matrix as a grid of integers, it is often convenient to display the label matrix as an image. One way to create such an image is to use the colorize function. The colorize function applied to a matrix displays the matrix using a contrasting color for each distinct element. So when displaying a label matrix, areas with the same color correspond to pixels from the original image that are in the same cluster. In many applications, it is useful to control both the number of segments and how pixels are assigned to those segments. Starting with controls for the number of segments, here is an image that could be segmented in several different ways, and this input uses the second argument in the clustering components function to specify that the segmentation should use at most 3 segments. The output is again a label matrix. This image happens to have dimensions 240 by 160, so the label matrix is a large array of integers that goes on for several pages. By default, a large matrix like this is typically displayed in a shortened form like the form shown here. You can click the buttons in this result to show more of the matrix, but it is probably easier to see the structure of that matrix by using the colorize function to display the matrix as an image. The colorized image for this segmentation shows the 3 segments. There is 1 segment for the background, 1 segment for the flowers in the foreground, and 1 segment for the leaves and other green colors in the image. A simple adjustment is to change the number of segments. For example, this input specifies that the segmentation should use at most 5 segments. Here is the colorized image for that label matrix, which shows 1 segment for the background, 2 separate segments for the darker and lighter parts of the flowers, and 2 separate segments for the darker and lighter shades of green. Inspection of the colorized label matrix is only one of many tools for working with the segmented image. Some things can be done using general-purpose programming functions. For example, here again is that same image segmented into 5 segments, and this uses the flatten and union functions to find out that the elements in the label matrix are the integers 1 through 5. This input uses a simple map program to replace all of the elements larger than 1 with 0 and then display the result as an image. The 1s in the label matrix correspond to the background of the image, so this result shows white for pixels that are part of the background. In the Wolfram language, rather than using general programming functions, many of these operations can also be done using more specialized functions, such as the component measurements function. For example, this input uses mask as the second argument in the component measurements function to get each component as a mask. The first argument in the component measurements function is the label matrix, and the second argument specifies the measurement to calculate. A mask is just a matrix of 1s and 0s with 1s for the pixels that are part of that segment. The masks are returned as sparse arrays, which for present purposes can be treated just like ordinary arrays. This displays the mask as images. The masks can be multiplied by the original image to pick out the corresponding segment of the image. Comparing those segments with the original image, we can see that the first segment corresponds to the white background, segments 2 and 4 correspond to the lighter and darker parts of the flowers, and segments 3 and 5 correspond to the lighter and darker greens in the image. The masks can also be used to perform separate operations on each segment of the image. For example, this input uses the mask to replace the white background with black. And here is a short program that replaces the background with black, adjusts the colors of the flowers, and leaves the green parts of the image unchanged. You can also select components based on component measurements. For example, this uses count as the second argument in the component measurements function to give the list of component labels and the number of pixels in each component, after which the select function is used to pick out components that have at least 8,000 pixels. Further programming could be done to pick out masks or to get a label matrix for the selected components, or this can be done using a function called select components. This uses the select components function to generate a new label matrix for components where the pixel count is at least 8,000. The result is a new label matrix where components that do not pass the specified criteria are replaced with zeros. Colorizing that label matrix shows that the selected components correspond to the flowers. In addition to choosing the number of segments, there are several other choices that affect clustering, such as the choice of method to use for clustering, the choice of formula to use for calculating the distance between pixels and color space, and the choice of color space. In typical cases, the distance between pixels is calculated using the ordinary Euclidean distance formula, which is applied to calculate the distance between points in the color space of the pixels. This diagram illustrates one relatively common clustering method called the k-means algorithm. The k-means algorithm operates in the color space of the pixels, so describing one pixel as being near to another pixel means that the colors of the pixels are similar, not that the pixels are near to each other in the image. The k-means algorithm is applied to an image by choosing some number k of points called centroids in the color space and then grouping each pixel with the nearest centroid, thereby creating one cluster of pixels for each centroid. Each centroid is then moved to the mean of the pixels in that cluster, and the process is repeated until every pixel is clustered with the centroid that is nearest to that pixel. In practice, this process usually converges in a few steps, although since every step in principle requires comparing every pixel with every centroid, the process can require a significant amount of computation, especially for images with a large number of pixels. Since any algorithm for clustering involves calculating the distance between pixels, an important way of controlling segmentation is controlling how those distances are calculated. For example, consider segmenting this image into 3 clusters. Since this image has 4 bars of color, clustering into 3 segments requires combining the 2 bars that are nearest to each other in color space into a single segment. This input uses the method and distance function options to specify that clustering should be done using the k-means algorithm, with the distance between pixels calculated using the Euclidean distance formula. Since this is an RGB image, that distance is calculated in the RGB color space. For this image, the bars with the nearest colors in the RGB color space are the 2 bars at the top of the image, so those bars are combined into a single segment. One way to change the segmentation is to change the color space. For example, this converts the image into the LAB color space. Now repeat the same segmentation with the image in the LAB color space. The bars with the nearest colors in the LAB color space are the 2 bars at the bottom of the image, so now those bars are combined into a single segment. The LAB color space is designed to approximate human vision and so is appropriate when segmentation should be based on human perceptual differences rather than differences in a color space like RGB. Here is a more realistic example that shows a similar effect. This is an RGB image, so this segmentation is based on distances calculated in the RGB color space. For comparison, here is another segmentation of the same image with the same k-means method, but with pixel values given in the LAB color space. The result is a different segmentation, since the change in color space changes the pixels that are considered nearest to each other in that color space. The best choices for color space, distance formula, clustering algorithm, and other variables depends on many details of your application and are often best identified by trial and error. That's the end of the examples for this section. To summarize, here is some of the vocabulary from this section. This section introduced clustering as a method of image segmentation, using label matrices to represent the segments or components of an image, and gave a few examples of controlling the number of segments and other variables in the clustering process. In the Wolfram language, segmentation by clustering is handled by a function called clustering components, which returns the image segmentation in the form of a label matrix. You can use general programming operations or functions such as component measurements or select components for further analysis of the segments.